So this is lecture 2.2. We have been talking about time response. In the last lecture, we saw a first order system, which was given by A divided by S plus A, and we subjected it to a step input. We saw the response in the S domain was A divided by S into S plus A, and after taking the inverse Laplace transform, the response came out to be 1 minus e to the power minus 8. We broke this response down into two parts. This one in green here is the forced response, and this this e to the power minus 80 in red here is the natural response. And we said that the overall response is equal to the sum of the forced response plus the natural response, which is given in black here. So in this case, we have written e to the power minus 80 as the natural response. To be more precise, we could write minus e to the power minus 80 as the natural response. In that case, the sketch would be slightly different. But in any case, in this case, we have the overall response as the sum of two responses, 1 and minus e to the power minus 80. Okay, so then we defined the time constant from this graph that we have of the first order system, which is equal to the time in which the natural response decays to 37% of its initial value, or the overall response rises to 63% of its steady state value. There is one more definition of the time constant, which is basically dependent, obtained from the rate of change of the response. So if you look at this response, Ct is equal to 1 minus e to the power minus 80, and we have already seen that the time constant is equal to the time t is equal to 1 by a, where Ct actually becomes 0.63, which is 63% of its steady state value. If you differentiate Ct, you will obtain a e to the power minus 80. And if you look at the value of this derivative at t is equal to 0, the value of this derivative at t is equal to 0 is equal to a, which means that the rate of change of the output at t is equal to 0, when it actually started changing, was equal to a. So if you draw a tangent here at t is equal to 0, and you look at this angle theta here, you know that the tangent is equal to the derivative. So your tan theta should be equal to a. The tangent at t is equal to 0 will basically be equal to a, because that is the derivative at t is equal to 0. Now the perpendicular here, this value is already equal to 1, right? So that means this value, the base here, has to be equal to 1 by a. So what does this imply? This implies that if the rate of increase at t is equal to 0 would have remained unchanged, then the response would have reached the steady state in the time constant, right? Because you can see from the triangle that the rate of change initially was this, and then it also started decreasing, right? But assuming that the rate of change remains unchanged from t is equal to 0, then from this line here we know that the steady state would have been achieved within a time much before the actual achievement of steady state. And what would that time be? That time would be equal to 1 by a. And what is 1 by a? That is the time constant. So the time constant, another definition would be the time in which the output achieves steady state had it increased at the rate at which it started to increase, right? Which is at t is equal to 0, is called the time constant, right? So that is why you see uh, this seems to be a technical, more sound definition as compared to saying that the output becomes 63% of its steady state value, or the natural response decays to 37% of its initial value. So this is another way to understand the time constant. So one of the uh, parameters for representing the time domain specification of the first order response is the time constant, and we have seen three definitions of time constant, right? The other uh, important parameter is called the rise time. Rise time is the value taken for this waveform to reach from 10% to 90% of its final value. So the time that it takes to move from 10% of its final value, which is 0.1 in this case, to 90% of its final value, which is 0.9 in this case, is called the time constant, is called the rise time. So if you have, for example, in this graph, if your point 1 is somewhere here and your point 9 is somewhere here, then this time between point 1 and point 9, this time between these two yellow lines would be called the rise time. So you can find out the value of the rise time by equating 1 minus e to the power minus at equal to 0.1, right? Finding the value for t here, and similarly equating 1 minus e to the power minus at to 0.9, finding the value for t. In this case, t is equal to 0.11 by a, and in this case t would be equal to 2.31 by a, and then you can subtract these two values. So your rise time would be 2.31 by a minus 0.11 by a, which is 2.2 by a. So for this first order system, the rise time is also a function of the time constant, directly dependent on the time constant. It is 2.2 times the time constant. Then you have the definition for the third important parameter, which is called the settling time. Settling time is defined as the time required for the response to reach and stay, right? To reach and stay within 2% of its final value. This is also called the 2% settling time, right? You can call this the 2% settling time. You can also have something called the 5% settling time. 5% settling time would be if you say that the time required is to reach and stay within 5% of the final value. That be the 5% settling time, right? So in any case, in general, we talk about the 2% settling time, and we call the settling time to be the 2% settling time. So Ct has to be equal to 0.98 for the first time, right? And you can equate this to 1 minus e to the power minus at, and once you do this and solve for t, you will get the settling time to be equal to 4 by a. So these are the three important parameters for describing first order response: the time constant, which is equal to 1 by a, the rise time, which is equal to, in this case, 2.2 by a, and the settling time, which is equal to 4 by a. You can see essentially that all these are functions of just one parameter, which is a in this case, right? Now, the second important, more complex time domain representation would be of a time domain response specifications would be of a system which is slightly more complicated than this, which would be a second order response, right? Second order systems, right? So what is a second order system? Again, when your transfer function, right, GS has a denominator, which is PS by QS, a rational function of S. In this case, the degree of QS, the denominator polynomial, is equal to Q2, then the system is called a second order system. Now, before we do this more generally, let us try to see what is going to happen for a typical second order system by straight away finding out the inverse Laplace transforms of certain second order systems, right? So suppose I'm subjecting them to step input. So suppose you have this second order system GS here, and you're subjecting them to a step input 1 by S, and you're trying to find out CS in this case. And suppose the first case, your GS, let us take a simple case. GS is equal to, say, for example, 9 divided by S square plus 9. It's a second order system because the denominator of the transfer function polynomial is of degree 2. So in this case, your CS is going to be 1 upon S square, 9 upon S square plus 9, and then you can take the you can try to find the partial fraction expansion for CS by writing this down as A by S and then plus BS plus C divided by S square plus 9. We write it like this because this is an order 2 polynomial, so you have to write BS plus C, and order 1 polynomial in the numerator. And when you solve for A, B, and C, you will get C of S is equal to 1 by S minus S upon S square plus 9. It is also evident because S square plus 9 and this S square are subtracted, and you get S square plus 9 minus S square, and you get 9 in the numerator. So this is your CS, and once you find out the inverse Laplace for this C of t, you get 1 minus, this is a cosinusoidal function, right? So this is cos 3t, 1 minus cos 3t. So the response is 1 minus cos 3t. So if I want to sketch 1 minus cos 3t, this is my CT, this is my time, right? So the time period at t is equal to, at what is cos 3t going to be? Let us sketch cos 3t. So this 2 at this is 2 pi f 2 pi by t is equal to 3. So the time period t is equal to 3 by 2 pi. So within 3 by 2 pi seconds, the cycle finishes, right? So you start from say 0, and then within 3 by 2 pi seconds the cycle would be over, and between at half of it, which is 3 by 4 pi, you will get the midpoint for the cycle. So if I want to sketch cos for this, this is going to be this is my cos, this thing in red is cos 3t. This is minus 1, this is 1. So at t is equal to 0, it is 1. At t is equal to 3 by 2 pi, did I do this correctly? Cos c at t is equal to 2 pi by 3. I should have written that. So 2 pi by 3, sorry. At t is equal to 2 pi by 3, I wrote it upside down. At t is equal to 2 pi by 3, this is 4, this is pi by 3, sorry. 2 pi by 3 divided by 2. At t is equal to 2 pi by 3, it is equal to, again, cos 2 pi, which is 1. At t is equal to pi by 3, cos 3 into pi by 3, which is cos pi, it's going to be minus 1. And between at pi by 6 and pi by 3 plus pi by 6, it's going to be 0. So this is the natural response for this function. Now, what is the forced response? The forced response is 1. So I can sketch 1. This is my forced response, right? Now this is the inverse of the natural response. I could have sketched minus cos 3t, which would have been maybe easier for me, because then I would have to add the two. Now I have to subtract these two. So if I subtract the green part and the red part, what will I get? So here this is 1 minus 1. It has to start from 0, so it will start from 0, right? Here this is going to be 1 plus 1, because this is 1 and this is minus 1 here. So at pi by 3, it's going to be 2. So I'll get something like this. Right? So do it once more. So this is like this. Right? So this is my response. This is my response. It is continuous oscillations. Continuous oscillations, right? So if I look at the system that I have, 9 by s square plus 9, it has basically, if I look at the poles for this system, s square plus 9 is equal to 0. I get s square is equal to minus 9, s is equal to plus minus 3j. So I have two poles, one at plus 3j and the other at minus 3j. Now this is one type of second order response. This is called the underdamped response. Underdamped, not the underdamped response, the undamped response. Undamped response, because there is no damping. Damping means that the oscillations should finally die out, but these oscillations will be continuously there in the system. So, so for a second order system given by this, subjected to the step input, we get a continuously oscillatory response given like this. Right. Now let us take another illustrative example, because it is easier to see this using examples. If I change my second order system slightly and I say have something like GS is equal to, say, 5 upon s square plus 5s plus 6, right? Now this, again, I'm subjecting to a step input. Rs is equal to 1 by s. And if I look at the pole locations for this, the s square plus 5s plus 6 can be written as s plus 2 into s plus 3, right? So the pole locations are like this on the s plane. There is, this is the j omega axis, this is sigma. So one pole is at minus 2, the other pole is at minus 3. Now what is the response going to be? So my output is 5 divided by s into s square plus 5s plus 6. I can break this down into a by s plus b by s plus 2 plus c by s plus 3. And I can find out the values for a, b, and c. So A is going to be, if I compare the numerators, I get A into S square plus 5S plus 6 plus B into S into S plus 3 plus C into S plus 2 is equal to 5. Now substituting S is equal to 0 in this gives me 6 times A is equal to 5. So A is 5 by 6. Similarly, I can find out the value for B by substituting S is equal to minus 3. So if I substitute S is equal to minus 3, I get A into 9 minus 15 plus 6. And I'll get a value of C for this, plus C into minus 3 into minus 1 is equal to 5. So this gives me this will be 0, this will be 0, and I'll get C is equal to 5 by 3. Similarly, I can substitute S is equal to minus 2 in this equation, and once I do that, I'll get B into minus 2 into minus 2 plus 3 is equal to 5. So this gives me B is equal to minus 5 by 2. So if I open this up, I get 5 by 6 upon S, and what is B? Minus 5 by 2 upon S plus 2. That is C is 5 by 3 plus 5 by 3 upon S plus 3. And now I can take the inverse Laplace for this whole thing. This is the CS opened up, and so I take the inverse Laplace for this. I get C of t is equal to 5 by 6 e to the power minus t. Sorry, this is 5 by 6 minus 5 by 2 e to the power minus 2t plus 5 by 3 e to the power minus 3t. So this is the sum of one constant term plus two exponentially decaying terms or increasing terms, right? Which both will finally decay to 0. So this is 5 by 3 e to the power minus 3t, whose final value is 0, starts with 5 by 3, and minus 5 by 2 e to the power minus 2t, whose final value is equal to 0. So the response is supposed to start from. So let us check whether we have done this right. So 5 by 3 minus 5 by 2 at t is equal to 0. 5 by 6 plus 5 by 3 minus 5 by 2, which is actually 6. 5 plus 10 minus 15. Yes. So the response starts at t is equal to 0. So the response has three parts. One is 5 by 6. The other is minus 5 by 2 e to the power minus 2t. And the third one is 5 by 3 e to the power minus 3. Now you can see very clearly that this is because of the pole at minus 2, and this is because of the pole at minus 3, and this is because of the input. So this part is the sum of these two is the natural response, and this is the forced response. And if you want to sketch all of them, so 5 by 6 would be something like this. So this is your 5 by 6, the forced response part, and minus 5 by 2 e to the power minus 2t. It's going to be it's going to start at minus 5 by 2 and then decay to 0, right? Because the initial value is minus 5 by 2. So this we say approximately somewhere here, right? Somewhere here, and then say it decays to 0 like this. So this is minus 5 by 2 e to the power minus 2. And then the third one is 5 by 3 e to the power minus 3t. So 5 by 3 would be roughly, say, let me wrap this one up. So it'll be somewhere up here twice than this, and then it is going to decay faster as compared to minus 5 by 2 e to the power minus 2t. It has a higher exponential decay, so it's going to be maybe something like, right? So this is just a rough sketch. So these are the three responses. If you add them up, right, you should get something like this, something that finally becomes equal to 5 by 6. So this is the total response. This is the total response. This is, these are your natural responses, and this one in black is your forced response. Now you can see this response, it slowly reaches the steady state value, and this kind of a response is called an overdamped response. It is the sum of two exponential terms. There is no oscillation. So we have seen two responses, two types of responses. So you can see that the response of a second order system is more complicated than the response of a typical first order system. So you have uh, an poles like this. This is undamped. And you have poles like this, right? This is overdamped. There are continuous oscillations in this. Your response sustained oscillations like this, and here your response is slowly increasing to reach the steady state. There are two more types to second order response to step input. We'll see them in the next lecture. Thank you very much.